Okay. Good morning, guys. As expected, the industrial project that we have requires you to design a lighting system for the building. So we're going to go on the roof, and we will be designing a lighting system, including the spikes or the lightning Air terminals. Thank you. You're going to correct me with all these terminology, and the cables in between them, and the grounding system. So we brought the experts in the industry, as we have done, guys, in the past. Thompson Lightning have been coming to Dunwoody for at least 10 years since I've been here at Dunwoody, and they put a great presentations about lightning. And today we have our expert here, Levi Carney. Did they say the last name right?
Yeah,
Carney.
perfect.
Mr. Carney is going to walk you guys through the lightning protection. So a couple of things. He has a handout for you. So when ready, I can pass the handouts, no problem, when you start.
Okay.
And also he will I will flash the AutoCAD later on our project, and he can give you some suggestions where to put these bikes.
Absolutely.
So it's all about lightning. Lightning is coming, I think, next week or the week after for the design. We do have FYI, we do have a family for the spikes that we use, the lightning terminal. We do have a family in Revit. We're using Revit now.
Oh,
so we will be dropping families on the roof, tying them with a cable, and put them down to the ground. So I'm going to let the expert talk about lightning. So thank you. I'll pass these. Go ahead.
Thanks, Chad. Well, like Chad said, I work for a company called Thompson Lightning Protection. We basically specialize in lightning and lightning protection for buildings. I've worked there for about 10 years now. And basically what we do, and we're local here in St. Paul, Minnesota, and we manufacture, engineer, and install lightning protection systems for buildings. So we pretty much do everything. There's a lot of lightning protection companies around the country, but there's only a handful that actually manufacture and install and go basically all the way with lightning protection. So I guess what I'm hoping to help you guys with is, obviously you have a building that you're going to need to design lightning protection for this semester. The packet that I put together should be pretty helpful. And like Chad said, you guys have all the details that we already gave you guys from Thompson's readily available on your servers. So when it comes time to do the design, you can just pull the details you want out for the building, and they should already be there.
Absolutely. We have three, we have three CAD files, guys, as we talk on the network, with all the lightning details and the notes that you need to attach to your Revit. So these are CAD formats. We will import them into Revit, and they will be standalone sheets later on.
So I think what I'd like to do today is just basically go over the basics of lightning so you can kind of understand that a little bit. I want to show you guys a video. It's basically put on by the Lightning Protection Institute, which is one of the main players in the industry. They also do a code book that we basically have to follow. Just basically then go from there to the design steps, which will help you guys design the system. I basically put 6 steps out there, 1 through 6. It should help you pick out exactly what you want, and it is very unique to the building that you guys have, that you guys are working on currently. And then any questions, if you have any questions anytime during this, feel free to ask. So I guess what I'd like to do is start with the video here. Hopefully it plays. Is the sound turned up on here?
Yep.
Okay.
Otherwise, we can go get it the old-fashioned way.
Yeah, for some reason the links break when you transfer it. I don't know why.
That's why they're just, no problem. Sorry for that.
No, that's okay.
Packing up to 100 million volts of electricity, lightning has the power to rip through roofs, explode walls of brick and concrete, and ignite deadly fires. Each year, thousands of properties are damaged or destroyed by lightning. A powerful strike can produce extensive property damage by sparking a fire or by surging through circuitry. According to Underwriters Laboratories, this force of nature accounts for more than $1 billion in annual structural damage to U.S. buildings. Lightning, by definition, is a discharge of atmospheric electricity from one cloud to another or from a cloud to the earth. When considering lightning, as it relates to lightning protection, it's important to keep in mind that this phenomenon is simply a massive spark of discharged electricity. A single bolt of lightning can generate heat in excess of 50,000 degrees Fahrenheit. If lightning's electricity is given a conductive path to ground to travel on, it will not cause damage. Lightning is tracked and mapped all over the world continuously by satellites. This map represents 5 years of lightning strike data for the United States. It's one tool to help us determine where lightning does the most damage, but it's important to keep in mind that often it only takes one lightning strike to destroy a structure. The National Weather Service describes lightning as the most dangerous and frequently encountered weather hazard that most people experience each year. Lightning protection provides security and peace of mind. The decision to purchase lightning protection is a lot like buying an insurance policy. It's not something you'll need every day, but it will be there to protect you, your property, personnel, and family when needed. Protecting people and property is what lightning protection systems are all about. This video was brought to you courtesy of the Lightning Protection Institute and your local LPI professional. The LPI conducts certification and educational programs and is a leading resource for lightning protection information and system requirements. Visit the LPI website at www.lightning.org for more information.
Chad, do you still have that box available of the parts that I left here? I think that's the only thing I forgot. So basically, that tells you a little bit about lightning protection and what I do. Basically, lightning is the only weather phenomena that we can actually stop and control. You can't stop it from happening, and I can't make it not happening, but it's the one thing that you can control where it goes. So unlike a hurricane or a tornado, this is the one weather that when it strikes, I can make sure it dissipates evenly and nothing ever happens. Most people don't put it on their house just because, like they said, it is an insurance policy. If lightning strikes your house, you know, your insurance company will cover any kind of damage. But the thing is, if lightning strikes your house and burns it to the ground, you know, this is actually a really cheap system to prevent that from happening.
Are you mainly in structural protection, or do you also do design for people that like circuit protection and things like that?
You know, there's really two ways, which is to protect the physical structure, which is what we do, and then the other thing is the surge protection, and that is basically, you know, all the way from surge protection to your front TVSS, you know, the main incoming electric, to your surge protection for your computers.
So you guys are structural.
We are strictly structural, and that's it. So we protect the structure from anything happening through a direct strike. Thanks, Chad. For the most part, this is all that's mounted to your roof. It's just a 12-inch copper air terminal. We have two different types, copper and aluminum, and I'll get into that a little bit later. But the whole system is its entirety is just consisted of a copper braided cable like this, an air terminal base that's attached to your roof, parapet wall, mechanical units, and then basically the cable is run around the building and then driven to a 10-foot ground rod on the outside. And essentially what our company does is create what's called a Faraday cage around the building itself. So if lightning strikes it, it creates a nice path around the building, around the outside, so nothing actually happens to the building itself. And I guess a little bit of the science behind a lightning strike is the moments before a lightning strike, and I'd say 75% of lightning strikes are actually cloud to cloud. Only about 25% of them actually come down and hit ground at a certain point. But what happens is, milliseconds before a lightning strike, they release what's called a step leader, and that step leader comes out. It was playing here. Yeah, the links are all. Sorry about this.
That was my fault.
Yeah.
My laptop.
For some reason, when you transfer the PowerPoint, it just breaks all the links.
Yeah.
Oh, yes. It's hard to see, but if you look over here, what's happening seconds before a lightning strike is a lightning bolt itself actually releases like a whole bunch of little fingers that are actually called step leaders, and everything that's connected to the ground has a positive neutron reaction, and up here there's a positive, and then there's negative in between, and that's kind of like a magnet pulling things together. So what happens is when you're standing on the ground, you have actually a positive ions coming off of you. And since the lightning strike, what it's trying to do is it's connect to the ground someplace. So when it actually releases that step leader and actually makes contact, then what it does is send the rest of the electricity through it. And I actually have a really good video in slow motion that shows a little bit more what that looks like. So basically, this video is milliseconds before a lightning strike. It's all in slow motion. So that's exactly what happens prior to a lightning strike. I hope this repeats. Basically, right here, it's releasing all these step leaders. Right now, they're desperately trying to get the ground. And the reason lightning is like this is because it's trying to find the easiest path to ground, the safest path to ground. So as it's going through the air, it's trying to find the safest, easiest path, and that's why it's actually shaped like a lightning bolt like that. And so those are called step leaders, and once it finds something on the ground, it connects with, that's when it releases the rest of the lightning. And like I said, only 25% of lightning is actually clouded ground.
So we deal with that.
So this was a house in Egan that got struck by lightning a couple of years ago. When lightning strikes a house without a lightning protection system, it can do a various number of things. It's extremely unpredictable. Sometimes when it strikes a house, it'll go through the phone line, blow the phone off the wall, and that would be it. Sometimes what it'll do is strike the house, end up in the rafters and start a fire like this one did. Sometimes when lightning strikes the house, it'll go through the cable TV and blow up the TV. It's really unpredictable. All it's doing is once it hits the house, it's trying to find the safest path to ground, wherever that might be, either a water pipe, a telephone, and it happens within a millisecond, and you never know what it's going to do. But there's one thing, if you put a lightning protection system on your house, it actually will protect it from any damage like this. Like they said on the video, this is basically the worldwide lightning strike levels. It's been tracked by NASA and Ocean, just a ton of different agencies. And they've actually come up with where the most of the lightning is. Obviously, here in America, we have what's called Lightning Alley in Florida, which has the most lightning in the entire country. And actually, there's a place in the Congo that has the most lightning in the entire world. Second to that would be a place in Venezuela and then Brazil. So you can see the density of lightning, where it occurs. Obviously, if you look at the map here, Washington, Oregon, California really has limited lightning, and our company doesn't do a lot of work out there. And the reason is people are willing to take their chance. There's places in Oregon that only have maybe one lightning storm every 4 years, opposed to someplace like Florida where they have something like 150 lightning strikes every square mile. So there's been quite a few myths, obviously, about lightning. As you can see, Zeus. The biggest myth would be lightning never strikes the same place twice. I always tell people and they always tell me, well, my house got struck by lightning, I never have to worry about it again. I always tell people, your house got struck by lightning, it's going to happen again. It's a really good indicator of you're in an area where lightning is present, and if it strikes once, a lot of times it's going to strike again. And the reason for that is you're just prone to a lightning strike. Maybe there's more thunderstorms a year. The Empire State Building gets struck by lightning 27 times a year. Once you put a system like this in place, it really requires no maintenance. Lightning doesn't affect it all that much. It could be up there 30, 40 years, and your house could actually get struck by lightning, 60 times a year without any issue. Second myth would be if it's not raining overhead, or there's not clouds overhead, basically I'm safe. Lightning can actually strike people from up to 8 to 10 miles away. So even though that storm is way off in the distance, it can travel a long, long way and actually hit a target where there's not even any rain or clouds. Second thing, obviously, if you're in your car, your rubber tires will protect you. Not really true. It's basically the car protects you because it's a metal cage around you. Rubber tires are not. You could have no tires on your car. When it strikes the car, basically, you're already in a metal cage, and lightning travels on the outside, so you're safe with or without tires. Unfortunately, this is how most people get struck by lightning and killed a year, which is standing underneath a tree. True that standing under a tree, you're not going to get struck directly by lightning. But what happens is when lightning strikes the tree, it actually comes down and it wants to side flash to you because you're a better conductor than the tree is. And that's how most people get killed each year. This one's just false metal on your body will attract lightning. Piercings, watches, nothing like that. Second myth would be lie flat on the ground. You never want to do that. When lightning actually strikes the ground, it does disperse. And there's been instances where lightning has struck a field and there's been 80 to 90 cattle that have all actually fallen over dead because the ground was wet and the lightning traveled into the ground and actually all the livestock was killed. This one unfortunately happens every year. A group of people are standing around, somebody gets struck by lightning, and basically nobody goes over there to help them because they think they're electrified. Once you get struck by lightning, there's all of it's dissipated. You don't have to worry about that person being electrified, so if they're on the ground, resuscitate them. This is probably the biggest thing that I run into as well, which is lightning rods on a building will attract lightning. Every time I put these on a building, people are like, well, now you're just attracting lightning in my building. And that's not the case. Whether this is up there or not, it's going to get struck by lightning. This actually does not attract it. It's just there to prevent. If lightning were to strike the building, it would have a safe path from it. This guy was struck by lightning in Florida. You can see by his hat. Basically entered his head, blew up his hat, it traveled down through his body. He still had the clothes he got struck by. You can see up there you have a 1 in 600,000 chance of being struck by lightning, opposed to winning the Powerball, which currently is 1 in 175 million. Men are 86% more likely than women to get struck by lightning. The reason for that is, I don't know. I'm thinking men who play golf are on ladders outside more than women. Even though you are more apt to getting struck by lightning as a guy, there really is only a 10% chance that you'll get killed. Even though lightning has such a massive voltage and amperage, it dissipates so instantly and it travels on the outside of your body that it doesn't have time to go inside and really cook your organs. So a lot of people that get struck by lightning end up with weird little scars on their body because lightning travels so fast it just kind of singes their skin. So luckily, 10% chance you won't get killed. So let's go into the design step. I just wanted to get into a little bit about lightning. This is the stuff that you guys really need to know about as far as designing the lightning protection system for your building. These are the 3 codes that I myself have to adhere to. And I think if you look in the packet, I included the LPI's code book here. So this is really good information when it comes to designing your guys' system. If you read through this, there's probably more than you'll need to know in here, but it's a really good indicator of where you need to place the air terminals, the ground conductors, and we'll go through that one by one here. So the first thing that you have to decide with your building is basically, is it a class 1 or class 2 system? What basically generates that is if your building is over or under 75 feet in height. And the reason for that is when you get over 75 feet, you need to use a larger cable size than a smaller one because lightning has to travel a further distance. 75 feet is the cutoff. They've done lots of experiments, lots of tests. Basically, your buildings, I think, are always under 75 feet.
Yeah.
So 30 feet,
Yeah.
so it's a two-story building. Okay, so your guys' system would be considered a class 1 structure.
Plus.
Yep. And so what you have here is the material list for your class 1, and this is basically broken out by copper, aluminum, which are the two different systems that we have. And I'll get into that a little bit later, but basically the minimum.
Yeah.
That's crazy.
You can grab the pen and hold it on it.
So 3/8 of an inch is the minimum material size for an air terminal. Which this is actually 5/8. So this one's a little bit bigger than the smallest one. The reason for that is lightning is hot and it is very powerful. If you go any thinner than this, what happens is when lightning strikes this, it can actually melt this. And if the cable is smaller than this, it can actually melt the cable as well. So that's why we have a lightning protection conductor that's braided, and that's a lot bigger than your standard electrical wire. So as an electrician, you're probably familiar with number 6 wires, number 4 wires. This is probably equivalent to like a 1-aught, which is a lot bigger than your standard electrical wire. And the reason is it has so many volts that have to go through it. So this list here goes into just a little bit about the copper conductors. Here is the minimum. Basically, it weighs 187 pounds per 1,000 feet. This is probably the number you guys would know more about, which is the circular mills. Each cable that you have has a amount of circular mills that can travel through it. Ours, the minimum here for class 1 is 57,400. Once again, it's a lot bigger than your standard electrical wire. And then it just goes through the rest of this. And all of this stuff is actually in your LPI book, and also in your design packet on page, about 6 from the back. So this is the other thing that you have to think about when designing your building. What to use on the roof system, copper versus aluminum. Aluminum is a little bit weird because if you were to mount like a copper material on aluminum outside of a building, they actually eat away at each other and corrode. So when you're mounting to an exhaust fan, typically they're going to be aluminum. So even though you can run your copper cable on the roofs, when you mount to a rooftop unit or a mechanical unit, they should be aluminum cable. And the reason is, over 10, 15, 20 years, they can actually start to eat away at each other. I have a couple of pictures. This was somebody who mounted the copper cable. It's a little hard to see on an aluminum roof. You can see how they're starting to corrode around here. And this was only after a couple years. If you were to leave this copper cable on this aluminum roof for, let's say, another 10, 15 years, it'll actually eat a hole directly through the roof. So when it comes to picking materials, it's very important. Copper's mounted to copper, aluminum's mounted to aluminum. Otherwise, you can see what happens. This was even, you can see where the cable's placed and where it actually is oxidizing. Anywhere in between or near this cable. Basically, the moisture, the air, all affect how the cable interacts with the material that you're applying it to. So that's this space here with an aluminum air terminal on it. Well, with copper. This corrosive area here, it's actually starting to eat through the roof. So it's just one thing to keep in mind is what kind of material you're using and what you're mounting to on your roof. The second thing would be you've got to ground your system. So what's the best way of doing it? Basically, if you have a brand new building, what we like to do is get the down leads concealed inside the building. The reason for that is you can hide it from the outside. It looks a little bit better. If your house is already up or your building's already up, we can route exposed on the outside of the building. But then again, will it work? Sure, but you'll see the cables all on the outside. So what we like to do is hide as much of this stuff as we can during the construction phase. So when it comes to spacing your grounds around the building, every 100 feet is probably where you're going to want to put the ground rods. Lightning basically needs two paths to ground. So no matter where it strikes on this building, it can go this way or this way. We have to, per code, put ground rods every 100 feet on center. So that's using full down leads. You can actually use the building steel. If your building is steel, then what we do is we ground the columns every 60 feet on center. And the reason is we need a little bit more grounds because the steel conductor itself is being used as the lightning protection down conductor, and there's more paths to ground. So since there's steel throughout this building, we end up almost doubling up the grounds in order to compensate for the lightning protection. Through roofs are still spaced at every 100 feet. So get a good picture. Basically, you're going to have a roof system that's mounted to the parapet wall, and then from here, every 100 feet is where you're going to want to go down the ground. If you look in your design package, it actually goes through all that in here. Yeah, page 6. So where we use full down leads instead of the building steel is always on concrete buildings, block wall construction, a wood frame house, hotels and houses, parking ramps, and those are the kind of structures that we space at every 100 feet around the outside. Typically, that's how we try to install it, and I think you guys have some CAD details of what that looks like on your system there. This is a boot that's usually provided by the roofing contractor. What we do is run PVC in the wall and try to hide it, and then we get out to ground. And what that does is allow the lightning protection system a safe path to ground. It's buried in the wall. Even though it's inside your building, lightning dissipates so rapidly that you actually don't have to worry about any sort of issue with lightning on the inside. The steel down leads, a lot of skyscrapers are made up of steel. The World Trade Centers, everything like that, were solid steel from the ground up. There's just no point in running a lightning copper cable down that when you've got steel that you can use instead of that. So what we do, instead of running this every 100 feet around the outside all the way down to ground, we actually just connected the steel because it works just as well. And it's so basically you're saving all that cable from top all the way down. Now, is your building a steel frame building, Chad?
Let's say concrete.
Is it concrete? Okay. And then this is basically what we put on the bottom of the steel columns at grade. You can either exothermically weld to it, or we have UL listed bonding plates that our company can provide.
So at the end of the steel building, you'd still drive. Okay.
Yeah, basically on a system like that, even though it's full steel all the way, it's going to be sitting on some sort of a concrete foundation. And so what we do is at the very base of it, we'll CAD weld to it or weld to it, and then still drive a 10-foot cradle. The other thing that you can do is, if your house is sitting on a cliff and you have really, really poor soil quality, is we run what's called a counterpoise system. And what that does is interconnect every single one of the ground rods in grade, and it gives you a little bit better of a resistance rating. A lot of houses in Florida do it just because they're sitting on, beach, just sand, which really isn't good soil quality for a lightning protection system. So we actually connect all the ground rods just to make it a little bit better of what we call an ohm rating, ohm resistance. Yeah.
Value that you can look for, like overall for a system, what like reach, resistance.
You know what? Surprisingly, there isn't any concrete number that you have to adhere to. A lot of owners want it to be under 5 ohms, and that is just personal preference. Our system, there's really no requirement. As long as you get your ground rods in every 10 feet, it's good enough for them. But yeah, a lot of owners want to get it under 5. Some of them are half an ohm or less, which is pretty rare and kind of hard to achieve. But in that case, what we sometimes do is instead of a 10-foot ground rod, we'll pound like a 40-foot ground rod, and we'll do them every 10 feet or every 20 feet around the outside perimeter, and we'll interconnect them all, and we'll bond the steel, and we'll add. It's just crazy. You can get into a lot of grounding. Is it good? Sure, but a regular lightning protection system will work just fine.
Please talk a little bit about
Oh yeah, actually I'm gonna get to that in just a second here.
If I can just inject one idea.
Yeah.
When we do like grounding for a building, guys, you're gonna have 3 grounding systems in every building. One for the low voltage, coaxial cables, the phones and so forth. One for the lightning, and one for the electrical system. So these 3 systems are interconnected, or the 3 systems could be one put together system. So that's why when you said 5 ohms, that's typical in the telecommunication industry for the towers. They require you to have 5 ohms or less. In the electrical code requires you to have 0.5 ohms or less.
Yep.
And if you can't maintain 0.5, you have to drive another ground rod. That's all they say. So there's a
and
more to grounding and bonding.
And that gets transferred over to us. They're like, well, I have to meet 25 ohms. Why don't you?
Yeah.
It's like my industry doesn't really, require an ohm rating. So they assume that because this says 5 ohms or this says 25s, that we have to adhere to that too.
Yeah.
Which is fine. I mean, it's just more material or something.
But here's what you can tell them. Tell them in the lightning industry, there's no circuit breaker that's going to trip when you hit lightning. The reason why we have this 5 ohms and 25 ohms is if you have a ground fault, and if it's high impedance to the ground, your circuit breaker is not going to trip fast enough. But you guys don't have a circuit breaker to trip.
We don't, which is why there's no requirement.
So
okay. That's good to know.
It has to do with the tripping of the circuit breakers and the blowing of the fuse.
Okay. And yeah, we don't have to worry about that because all of ours is basically, dead wire until it gets activated. The other thing you can do is drive a ground plate instead of a ground rod. It's not the preferred method, but like I said, if your house is located on a cliff and there's just no way to get a ground rod in, let's say you're sitting on 100 feet of bedrock, you can throw a ground plate in as well. That should disperse the lightning as well. This is just a ground test well. Basically, what you can do is place your ground rod in here, take this cover off, disconnect the ground, and actually do a 3-point follow potential on that ground rod to see what kind of ohm rating you're getting. And these are the different ways that you can connect to it. Typically, what we do is only mechanical or exothermic. This is how we attach to a ground rod. It's obviously a UL listed product that our company creates. This is exothermic welds, which I don't know if you guys are familiar with. Thermal Weld makes a lot of them. Erico, pretty much the big electrical companies actually make these. And what they do is you just take the cable, put it together, you drop your weld mold in there, and what they have is a little bit of gunpowder on the top of it. You spark it up, the weld metal melts, basically fusing together the cable. It's just another way to basically secure the lightning protection. It's either welding or mechanical. It's pretty typical.
And all these methods, guys, are approved methods for grounding your sort of system for electrical. So it's the play, it's exactly what you're saying.
Yep, in the electrical, actually, they have another one. You can use high compression, burn-y fittings, which is typically not approved for lightning protection. So these would be the only 2 that we can use, but electricians use these 2, plus they can use that high compression fitting. We also bond the water, gas, electric as it comes into the building. The reason for that is you need to equalize the potential. Even if this cable and a 10-foot ground rod is a decent conductor, what happens is it might flash to the water pipe because the water pipe is 1,000,000 miles long and actually might be a little bit better of, conductor. So what we do is just equalize the potential so when lightning hits, it dissipates evenly. So step 5 would be what I consider the zone of protection. I usually work from the ground all the way up. So step 6 will get into a little bit more of the air terminal placement on your roof. This is what our industry considers which roof levels need lightning protection and which roof levels don't. Obviously, if you have a skyscraper, does a little tiny shack next to it need lightning protection? Probably not. And there is actually a way you can calculate it. I don't know if you guys are familiar with CAD, but basically if you were to draw a 300-foot tall giant rolling ball, this is what it would look like. What you can end up doing is just take that ball, push it up next to the building, and I can guarantee without any instance that this area here that's hatched will not get struck by lightning. It's a mathematical equation. They've done extensive research on it to where lightning actually hits. If I have an air terminal up here, there's an arc that it creates to ground where there's no way lightning can actually hit. So that's how we decide what zone of protection you get from higher adjacent buildings. And this is just a little bit more of an easier diagram. Basically, the easiest way to calculate it, if it's over 25 feet tall your building is, you can use a 1-to-1 ratio. 25 feet or less, 2-to-1. So if the height of this building is 40 feet, the height of this building is 10 feet, you can actually go out a total of 30 feet. So that's an easy way to calculate your zones of protection. So this would be the last step, which is where you guys are going to place your air terminals on the roof. This is probably the hardest to go through, but the most important. Air terminal placement, where you're going to route your cables, where you're going to place your through roofs, what kind of mechanical equipment you guys protect, and how you attach the cable to the roof. This is probably the most standard of details that I use on a daily basis. Basically, it's just a parapet base that's mounted to the outside edge of the building. Since residential construction, we probably only get into maybe 5 to 10% of the time. The majority of the work that we do, 90% of it, is actually commercial buildings. With commercial buildings, you get parapets, and a lot of parapets. Most standard outside edge of a building, this is standard parapet base to attach to it. And you guys have all the details that you can use. Basically, you just screw it into the coping on the outside of the building, and then string your cable in between. It's very important. Air terminals must be spaced every 20 feet on the outside of a building. And they must be within 2 feet of the outside edge. What you end up doing is starting, when you place your air terminals on your building, you start on the corners of the building and then work your way in between every 20 feet. Even on a flat area of the main roof, those air terminals are spaced every 50 feet. Any
on the perimeter, correct? Or you know,
20 feet around the perimeter, 50 feet around the inside of the building. When you look in this packet, there's actually little diagrams of where they need to be placed. Any mechanical equipment that you have on the roof also needs to be protected. It is subject to a direct strike. Basically, this is just a standard exhaust fan detail with an air terminal on top of it, connected to, as you can see, the lightning protection system here. Most people don't even know that a building is even protected with lightning. When you're standing on the ground looking up, you can rarely see it. This is another big thing. Any metal object that's on the building and within 6 feet of the cable needs to be tied to the system. The reason for that is 6 feet is the magic number. If lightning is traveling through this conductor, any metallic object within 6 feet actually risks having a side flash. If you don't equalize the potential between the two, basically it'll side flash here. Decide to use this as the downlink to ground, and then go throughout your building and wreak havoc. So what that does is tie the two together. This is something we do in the field. Lightning has a hard time turning sharp corners. So what we do is make a gentle 8-inch radius bend. Lightning strikes here and needs an easy path to ground. Lightning travels extreme speeds. If lightning were to strike here, it doesn't have time to make this sharp turn. It's actually just going to keep shooting off of the cable. So what we do is try to make the bends as easy as possible. So these are good diagrams of where you need to put the air terminals. Basically, it shows everything. You have to be 10 inches above the object that you're trying to protect. You have to be within 2 feet of the outside corners. You have to be within 2 feet of the outside ridges. And then these diagrams show you how to do it on a parapet, a flat roof, a ridge, and then the corner. So this is what we did on a project here locally. I took the tape measure out. You can see the air terminal itself is placed at 20 inches, which is sufficient to be within 2 feet of the outside edge. And once again, when you're standing from the ground, you'll probably never see this air terminal, just because we try to set it as far back as possible, so not to mess with the aesthetics of the building.
Is the air terminal glued?
Yeah, it can either be glued to a roof, which in this instance here, you can see the glue actually kind of seeping up to the holes here. So that's why our bases are made with the holes in here. We actually use an epoxy and set it down, and it sets within a couple days. Or you can use a screw base like this and screw it into the copings. So if you're mounting to a metal roof, you never want to screw to it, so we end up gluing to it. So these are the mid-roof air terminals that I was talking about. You space them every 50 feet on center. The reason we use these ones on the middle of the roof is if somebody actually falls and stabs himself, it basically bends backwards. So it's kind of an OSHA, approved air terminal here. So that's the reason. Those are spring points.
So they can't make a movie with that.
That's right. The other part of the system is the cable and how to secure it to the building. Once again, you can glue it or you can screw it to the building. Code states it has to be secured every 3 feet on center. The reason for that is a little bit of playing the cable on a windy day can start to move, and what happens is it starts to chain react, and you'll actually start pulling all these clips out if it's secured, let's say, every 20 feet on center. So what we do is screw it to the copings or glue it down every 3 feet, holds it in place, and the cable won't go anywhere. So that's what a typical cable holder looks like on a flat roof that we glued to it. You can see it's just basically a stamped piece of brass that holds the cable. It's glued to the roof. The adhesive sets in, and we run the cable right through it. Top left there is a picture of a loop clip that we use. Screw it to a coping. You can screw it to a shingle roof. Either method works just fine. Basically, lightning runs a lot like water. The reason is lightning can't go uphill. Water can't go uphill. So when we're taking our lightning systems, what it's going to ground. Much like water, you're not going to run the piping back up and over. Lightning is the exact same way. So what we do is every time that we come down, it has to continue going down. So if you run your cable or your lightning, it's just like water. You want it to flow downwards. There's no way it's going to flow uphill. That's what a typical through roof on a building looks like. Basically, the cable is routed along the outside. We've got the air terminals up here. The cable connects from this cable splicer here into the PVC, which is a part that we specially made up, and then the cable goes down to ground. That's how we get things from point A to point B inside the building. I guess the last thing I want to touch on, and I just want to do this real quick, is what's called an ESE system. It's called an early streamer emission. It's not part of the industry standard. a lot of people are using these things and telling people, the ones who sell them say, I can put this one lightning rod on your roof and it's going to protect the entire thing, which is actually a false statement. So if you see one of these, you know, a lot of engineers do get hooked onto buying these things. The thing is, a standard lightning protection system is every 20 feet on the outside and every 50 feet on the middle. One of these, unfortunately, and I wish it was the case because it'd be a lot cheaper and easier, if you could put one of these and it would protect the roof. Unfortunately, that's just not the case.
So these aren't UL listed.
They're not UL listed, and none of these LPI, UL, NFPA will certify. And they've done extensive tests on if they work or not, and they've just failed everything. That's it. Any questions? Yes.
You had a air handling unit on top of a roof.
Mm-hmm.
It wasn't farther than 6 feet away from your bathroom ever. You wouldn't have to bomb that. And there's like in the middle of the.
No, you still would have to put air terminals on it, because now it's typically the highest point of the roof. So basically, the 6-foot rule is just for roof drains, little plumbing vents, stuff like that. The bigger mechanical units still need air terminals on them.
If there's like a radio tower, but that was like the highest point of the roof,
Mm-hmm.
or like maybe structural heat, and the air handler unit was underneath that, to be okay.
And then you could run what's called the zone of protection. And if it falls within the zone of protection, then you're right, you won't need
That's that 150 radius.
exactly. Yep. If it falls within there, yeah, you don't have to do anything with it.
So you said that your company goes out to Florida. You guys go out to Florida too?
Actually, Florida's the one state we actually have 3 companies that we hired
Oh,
that work for us. So they do all the work in Florida.
okay.
Yeah.
Just off the ball, what's like the highest and lowest number, like the high rise versus the residential cost of the system?
It's a good question. I typically tell people, if you want to get a lightning protection system on your house, and we're not talking a James J. Hill house, I mean just a standard, you know, let's say 2,000 square foot house, you're looking at anywhere between 25 and $5 grand. The World Trade Centers, we currently have the contract for all of those, and a project like that can be upwards of $200,000-$300,000. So there is a wide range in between. You know, houses are pretty cheap. This is when you get into the bigger projects, they can get quite stuff.
You will say a few things about how you guys interface with Michelle Fuller Erickson or the engineering firms.
Oh, yeah.
Hire you to do things a few words.
Yeah, we work with a lot of the engineering firms around here. What they do is a lot of times they'll get plans for a building, and prior to releasing it for bid date, they contact us and they're like, hey Levi, can you do a system for this building so I can put it in the bid package, so when it comes time for bid, you know, we have a system in there that's already been designed by you guys that we can just submit. So yeah, a lot of the companies, TKDA, Michaud Cooley, a lot of those companies hire us to do the lightning protection layouts for their bid packages.
Have you guys been doing Revit? Anything in Revit?
You know, we haven't. We've done a couple full 3D models in standard AutoCAD,
Okay.
but we haven't done Revit yet.
You haven't been asked to add your stuff into a 3D Revit model yet?
We have, and we did it in AutoCAD.
Okay. Somebody must have put it in the system.
Somebody must have taken our system and then
Yeah.
transferred it to Revit. But yeah, I mean, in order to do a lightning protection system in Revit, it would take a long time. It really would. I'd love to, because it would look great and you could see exactly how it goes from point A to point B. Typically what we do is just 2D isometric drawings. You know, show a picture of the detail and where it applies on the roof.
The way we're doing it right now is we have a family that we drop for the lightning terminal,
Mm-hmm.
and then we connect them by dotted lines. We really don't put a cable, so to speak. So we're doing
Oh, okay.
kind of we drop a family that looks 3D family, and then
Sure.
we connect them with dotted lines.
And that's pretty much what we
And
do.
it looks, when you print it, it looks exactly like your CAD drawing,
Okay.
but we don't put a cable, so to speak. So that's what probably most of the industry have standardized at least.
Yeah. And that's basically what we do in AutoCAD.
It just looks, it's a CAD look in Revit.
Yeah, exactly.
So to speak. Do you guys have any questions for our friend here? We're gonna be doing, I don't know if we told them about the package that we have. We have a complete package, guys, for you. I think the most important thing, correct me if I'm wrong here, is when you place your Lightning terminals. I have to remember the Lightning terminals. And by the way, these are donated to us. You feel free to come over here and look at them. They're in my office all the time and leave them here. When you place these guys, especially where this one, right here, we place them 20 on center.
Yep.
Around the parameters. That's, you have to remember that when you place yours. 20 on center around the parameter. You can't place them more than 2 feet away from the edge of the what do you call that? The wall. So it has to be somewhere here within that 20 feet, within that 2 feet. 20 feet to the center is what you need to remember. If you put them in a building, inside the building, in the middle of the building, 50 on center, right?
Yep.
That's another number you have to remember. 50 on center, inside, in the middle of the building. 20 around the parameters. And when we drop, we take a wire down into the ground rods. We put our ground
100.
rods 100 on center. So you put ground rods 100 center on the buildings, and you make a drop every 100, I believe.
Yep.
Every 100 feet, you make a drop from the roof down into the ground rods. That's really the bottom line. We do have a family in Revit for this baby. The rest of the stuff we do it drafting in Revit. We draft the ground rods and we draft the cables and so forth. We also have three AutoCAD files with all the details that Levi was talking about. 3 AutoCAD files, every single detail that you saw, and now we have it in CAD. What we have done in the past, guys, we import them into Revit and we print them as detailed, Lightning details. So that's what we have done in Lightning. We do have in our project, if I might inject, also guys, if you look at the roof of our project, we do have 5 things on the roof that you have to also put a spike right at the top of them. We have 5 exhaust fans. So every exhaust fan on the roof is going to have one of these right at the top of the exhaust fan tied to the system. And we also have a cooling tower. And the cooling tower, what we've done in the past, a cooling tower is a big object. I don't know, probably it's going to be 10 feet by 4 feet. And the height probably going to be another 10 feet. So what we did in the past is we put one Lightning like this baby on every corner of the cooling tower. So we'll have 4 on the cooling tower. That might be overkilling, but
No, that's exactly how you're supposed to do it.
so these are the things that you have to keep in mind. Lightning will be in a couple of weeks when we do the design for it. So, and you guys, I believe you are going to be presenting about the Lightning. Are you? I thought we assigned the Lightning to somebody. Yes, Lightning.
Basically, how many other stars do we have?
How many air terminals on a building?
Yeah.
It's all different it all depends on the building that you're working on, the size of the building. So it changes every time. Every building is completely unique. So typically what I do is put an air terminal on every corner and then just every 20 feet in between.
Is there I know when you estimate the project, is there kind of an estimate to go by air terminal? How do you go about your estimation?
Typically what I do when I get a building is I grab the roof plan, I grab the elevations, I take a look to see what it looks like, and then I just do a hand sketch real quick where I know everything's supposed to be, and then I just count it up and put it in a quote.
Okay.
So basically what I have to do is lay out the system every single time I get a building.
I see.
Each building is completely unique.
Any question guys about Lightning? We're going to keep these. These are ours to keep for the last 10 years at the end. Feel free guys to look at them, feel them if you haven't done them. We are scheduled to visit Allianz data center right here, 10 miles away or 5 miles away from us. When we go there, guys, they give us a tour of their roof, believe it or not.
Oh, really?
So we go on the roof and you see the air handling unit, mechanical equipment. That's the part of the tour. But the other part is you will see all these Lightning terminals. Lightning terminals around the perimeters of the building. It's really I thought it was unique, as well as the cables and how they put the system together.
The difference between a lightning rod and a lightning terminal?
No, same thing.
Technically, this the terminal, right?
It's supposed to be an air terminal.
Air terminal.
Most people call them so, lightning rods. Yeah, my business card is in each one of those packets. If you guys have any questions whatsoever, feel free to email me. If you need a detail, I can send it over in CAD. If you need help designing it, I'm there for you. So if you have any questions, just let me know. Email's attached.
Okay, thank you.
All right.
Appreciate it.
Thank you, guys.